deep dive. This is a really interesting one today.
It really is. We're not just looking at a theory, are we?
No, not at all. We're watching a fight.
Yeah.
A 50-year intellectual battle, really.
Yeah, the ultimate physics clash. You've got general relativity on one side
Einstein's masterpiece, gravity as geometry.
and quantum mechanics on the other. The rules of the very small.
And they meet head-on at the black hole, and it's like the foundations of reality start shaking.
It's definitely the most, let's say, high-stakes puzzle in physics. It really forces scientists to question their own fundamental laws.
And it all revolves around black holes, these just incredibly extreme objects.
Exactly. The place where gravity goes haywire.
So today we are plunging deep into the black hole information paradox. It's this crisis that's been simmering, boiling really, since Stephen Hawking's big calculations back in the 70s.
Right, and you sent over this amazing pile of sources. We've got the history, the core conflict between GR and QM.
Yeah, the story of the black hole war itself, Hawking versus Susskind and 't Hooft.
Giants of physics really duking it out. And fascinatingly, the sources cover the modern resolution, which only really clicked into place, around 2019?
Pretty recently, yeah. So our mission here, for you listening, is to really unpack this. We need to get into why quantum mechanics insists information can never be lost.
Why it has to be eternal.
Exactly. And then why black holes, according to gravity, look like the perfect information shredders.
The ultimate cosmic delete button.
And the big payoff. How did physicists finally solve it? How did they, as Leonard Susskind put it, make the world safe for quantum mechanics?
It really boils down to this. GR says information falling into a black hole is trapped, gone forever from our universe, hidden.
But QM says, nope, information cannot be destroyed, ever. It can only be, rearranged.
So the paradox hits when you realize black holes aren't forever. Quantum mechanics itself says they evaporate.
Hawking radiation, they shrink and disappear.
So what happens then? Does all that information, the history of everything that fell in, just vanish, poof, erased from existence?
That's the core question. Let's dive in. Okay, so to really get this, we need to build it up piece by piece. Let's start with pillar number 1, general relativity. Einstein's view. This is gravity's prison.
Right. Before we even touch quantum mechanics, what does GR tell us about black holes and information?
In GR, it's just such a different way of thinking about gravity.
It really is radical. Forget forces pulling things. Einstein said gravity is the shape of the universe.
Matter and energy warp space-time. They curve it.
Exactly. And that curvature tells everything else how to move. It's all geometry.
And black holes are the most extreme prediction of this warped geometry that we've actually confirmed exists.
They absolutely are the ultimate expression of space-time curvature.
So what makes it a prison in this GR picture?
It comes down to its key features. The most famous one, obviously, is the event horizon.
Right, the point of no return.
Yeah.
But it's not like a surface you can touch, is it?
No, not at all. People often picture that like a hard shell. It's purely a boundary in space-time, a causal boundary.
Causal boundary. Unpack that a bit.
Okay, think of it like this. Space-time itself is flowing into the black hole. Near the black hole, this flow gets incredibly fast.
Faster and faster as you get closer.
Right. The event horizon is the specific distance from the center where that inward flow of space equals the speed of light.
Wow. Space itself is pulling inward faster than light can pull outward.
Exactly. So if you're inside that horizon, even if you shine a flashlight directly outwards, the light ray gets dragged inwards because the space it's moving through is falling in faster than the light can travel.
So anything that crosses that line, trapped forever.
Forever cut off.
Okay.
Causally disconnected from us, the distant observers.
Yeah.
Any information it carried, its history, its quantum state, it's all stuck inside. Hidden.
Yeah.
At best.
That's the trap.
Yeah.
Okay, and then deeper inside.
Deeper inside, GR predicts the singularity.
The infamous singularity.
Yeah. Where all the matter that collapsed to form the black hole gets crushed down to a point of zero volume and infinite density.
Which is basically physics code for our equations breakdown here.
Pretty much. GR itself ceases to make sense at the singularity. In a purely classical picture, you could argue the information is just obliterated there, or at least rendered completely irrelevant to the outside.
But the classical problem that really sets the stage for the information paradox even before evaporation is this weird simplicity of black holes, the no-hair theorem.
Ah, yes, the no-hair theorem. Crucial piece, developed by people like Werner Israel, John Wheeler. It's the classical basis for thinking information might be lost, or at least hidden incredibly well.
So what does no hair mean? It's such a great name.
It is a fantastic metaphor coined by Wheeler. It means a stable, isolated black hole is incredibly simple when viewed from the outside. It's defined only by three things you can measure externally.
Just three. What are they?
Its total mass,
Yeah.
m, its total electric charge, q, and its total angular momentum, j, its spin.
Mass, charge, spin, MQJ. That's it.
That's it, according to the theorem. Everything else, all the complex details of whatever fell in to make the black hole, that's the hair.
So the hair is like whether it was made of hydrogen gas or diamonds or copies of Wikipedia.
Exactly. Imagine one black hole formed from a collapsing star of pure hydrogen. Another one, same final mass, charge, and spin, but formed by collapsing, say, a planet made entirely of complicated organic molecules, or a whole library.
The hair is all that specific information, the arrangement of atoms, the quantum states, the sheer complexity in history.
Right, and the theorem says that as the black hole forms and settles down, it radiates away all that complexity, all that hair, mostly through gravitational waves. What's left is just bald,
Yeah.
characterized only by M, Q, and J.
So looking from the outside, you absolutely cannot tell if the black hole ate the hydrogen star or the library.
Not according to classical GR and the no-hair theorem. The information about the origin is completely hidden behind the event horizon, homogenized.
Now, in a purely classical universe where black holes live forever, maybe this isn't a paradox.
Right? It's just inaccessible information. It's locked away permanently, but you don't have to worry about it being truly destroyed because the prison lasts forever.
It's permanent confinement, not deletion.
Precisely. The crisis, the paradox, only ignites when quantum mechanics enters the picture and tells us the prison isn't permanent, that the black hole evaporates.
That's what turns this classical hiding into a potential cosmic crime of information destruction.
But it's interesting, the sources you shared point out something important. Even this classical pillar, the no-hair theorem, isn't totally unchallenged anymore.
Oh, even before the main paradox resolution.
Yeah, way back in, well, not way back, but in 2016, Stephen Hawking himself, with Malcolm Perry and Andrew Strominger, published this really significant paper.
What did they propose?
They argued that black holes actually do have a kind of hair, but it's incredibly subtle. They called it soft hair.
Soft hair, like low energy.
Exactly. Zero energy quantum states. Soft gravitons, soft photons that linger right at the event horizon. Yeah. And they argued these soft fields do encode information about what fell in.
So they were suggesting that maybe black holes aren't perfectly bald after all, even classically if you look closely enough at these quantum effects at the edge.
That was the idea. It hinted that maybe the information wasn't entirely lost behind the horizon, but somehow imprinted right there at the boundary.
Interesting. So even the classical foundation had some cracks appearing, suggesting the final answer would need to blend the theories, not just pick one.
Definitely points toward the synthesis, yeah. The seeds were there.
Okay, so GR gives us this picture of an information prison, simple on the outside, trapping everything inside. Now bring in the other giant, quantum mechanics.
And here's where it gets really, really weird and fundamental. Because QM has a completely non-negotiable rule about information.
It insists information is eternal, absolute. It cannot be destroyed.
Cannot. Full stop. This isn't just a preference. It's woven into the mathematical fabric of the theory. Violating it breaks everything.
And the technical term for this bedrock principle is unitarity.
Unitarity, yeah. It sounds abstract, but it's the mathematical property that guarantees the quantum world behaves predictably and causally.
So what does unitarity actually enforce? What are its concrete consequences?
Okay, so unitarity governs how a quantum state evolves over time. Think of the Schrödinger equation, the master equation of QM. Unitarity ensures that evolution is smooth, continuous, and reversible. This leads to three critical rules.
Rule number one.
Probability conservation. In any quantum process, the probabilities of all possible outcomes must always add up to 100%. If unitarity failed, probabilities could leak away or pop into existence from nowhere. You could end up with 99% or 101% total probability.
Which would mean things could literally vanish or appear randomly. That breaks basic conservation laws like energy conservation.
Exactly. It's deeply tied to conservation laws. Which leads to rule number two, arguably the most important one for the paradox. Reversibility.
Reversibility, meaning you can run the clock backwards.
In principle, yes. If a process is unitary, it means if you knew the exact final state of a system, every detail about every particle, you could use the laws of quantum mechanics to perfectly calculate what its exact initial state must have been.
Like watching a movie in reverse, and it still makes perfect physical sense.
Precisely. It's a perfect two-way street, mathematically speaking. No information is lost along the way that would prevent you from reconstructing the past from the present.
And that directly implies rule number 3, information conservation.
Right. Because if the process is perfectly reversible, it means the total information content, the complete description of the quantum state, can only be transformed or scrambled. It can never be created from nothing, and critically, it can never be destroyed into nothing.
It can change form, get hidden, get spread out, but the total amount of information stays the same.
Always. Losing information fundamentally breaks reversibility, and through that, unitarity. It's why physicists guard this principle so fiercely. It's tied to the predictability of the universe.
Okay, this distinction between information being scrambled versus truly destroyed is absolutely key. Let's use that classic analogy, the burning paper.
Ah, yes, the burning paper. Perfect illustration. Imagine you write down something secret like, I don't know, your bank password on a piece of paper.
Okay, password 123, written down. Now I set it on fire.
Whoosh, it burns. What are you left with?
Ash, smoke, heat, some light. For all practical purposes, my password is gone. The information is inaccessible, scrambled into gunk.
Right. From our everyday perspective, the information is lost. But unitarity makes a much stronger claim. It says that in principle, the information is still there.
How? Where? In the smoke particles.
In the exact quantum state of every single particle that results from the burning, the precise position, momentum, spin, energy level of every molecule of smoke, every atom of ash, every photon of heat and light emitted.
So the final state is incredibly complex, but it's uniquely determined by the initial state, the paper, the ink, the oxygen, the match.
Exactly. An observer with godlike abilities. Someone who could capture and measure every single one of those resulting particles could, in theory, apply the laws of quantum mechanics in reverse and reconstruct the original state, including your password.
Wow. Okay, so the information isn't gone, it's just smeared out across countless correlations in a very high-entropy, messy state.
Perfectly put. It's scrambled, hidden in correlations, but conserved. Now apply this to the black hole.
Okay, so the classical no-hair theorem already told us the information is inaccessible, hidden behind the horizon. Like the password after burning, practically lost to us outside.
Right, but the paradox comes when Hawking brings in evaporation. The claim becomes that black hole evaporation doesn't just scramble the information, it suggests it's destroyed in principle.
Meaning it violates that fundamental quantum rule.
It implies that if you started with two different initial states, say, our hydrogen star versus our library, collapsed into identical black holes, they would both evaporate and produce the exact same final state. Just random, featureless thermal radiation.
Wait, if the final state is identical for two different starting points.
Then the process is fundamentally irreversible.
Hmm.
You can't run the clock backward from the final radiation to know whether it started as a star or a library. The history is erased, wiped clean.
That's the violation of unitarity. That's the catastrophe.
That's the core of the paradox.
Hmm.
It suggests the laws of physics contradict themselves at the intersection of gravity and quantum mechanics. Something has to give.
So we've got GR building the prison, QM demanding information freedom. The tension was there, but it absolutely exploded in 1974.
That's the year Stephen Hawking dropped the bombshell. He did the calculation that brought quantum mechanics directly into the black hole's domain.
And the result was, revolutionary doesn't even cover it.
No, it changed everything. He showed that black holes aren't truly black. They have to radiate energy. They glow faintly.
Hawking radiation. And because they radiate energy, they must have a temperature.
Right. This was the first concrete prediction where GR and QM had to work together. And the result was this paradox staring us in the face.
Okay, before we get to the paradox implications, we really need to dig into how Hawking radiation actually works. Because the popular explanation, it's everywhere, but the sources you shared were really clear that it's misleading.
Oh, the virtual particle pair thing, yeah, where one particle falls in, the other escapes.
Exactly. It's a nice visual, maybe, but apparently it's just not accurate physics. A fantasy, one source called it.
It really is. It misses the subtlety and the power of the real mechanism, which comes from quantum field theory, or QFT, in curved spacetime.
QFT in curved spacetime. Okay, let's break that down. What's the core idea?
The key insight is that the very concept of what constitutes a particle is not absolute. It depends on the observer, especially in strong gravitational fields.
So different observers can disagree on whether particles exist or not.
In a sense, yes. Particularly, they can disagree about the vacuum state, what empty space looks like.
How does that work near a black hole?
Okay, QFT tells us that even empty space, the vacuum, is full of quantum fields constantly fluctuating. Now, near a black hole, space-time is extremely curved. And crucially, time flows at drastically different rates for different observers due to time dilation.
An observer falling in experiences time differently than someone watching safely from far away.
Massively differently. So imagine an observer freely falling past the event horizon. According to Einstein's equivalence principle, they should feel like they are in normal, flat space-time at that moment. They see the vacuum around them as empty, calm.
Okay, nothing weird for the infalling guy.
But the distant observer sees things very differently. Because of the extreme curvature and the intense time dilation near the horizon, the quantum fields get distorted from their perspective. What looks like a calm vacuum to the infalling observer looks excited to the distant observer.
Excited how? Like particles appearing.
Exactly. The mathematical process ascribing this difference in perspective is called a Bogoliubov transformation. It shows that the state the infalling observer calls vacuum is seen by the distant observer as a state containing a steady, continuous flux of thermal particles radiating away from the black hole.
So the Hawking radiation isn't particles popping into existence at the horizon. It's more like the distant observer perceiving the vacuum state near the horizon as being full of particles because of the warped geometry and time.
That's a much better way to put it. It's a consequence of how quantum fields behave when space-time itself is so dramatically curved. It's a real energy emission from the distant observer's point of view.
And if real energy is being radiated away,
Then the black hole has to be losing mass. Einstein's seesaw tells us energy and mass are equivalent. So the radiation carries energy away, the black hole's mass decreases.
it shrinks. Slowly at first, but it shrinks.
Yes, and here's a weird twist. The smaller the black hole gets, the hotter it becomes and the faster it radiates.
So it accelerates its own demise.
Exactly. A stellar mass black hole takes an unimaginable amount of time to evaporate, far longer than the current age of the universe. But eventually it would shrink, get hotter and hotter, radiate faster and faster, and finally disappear completely in a final burst of high-energy radiation.
Poof. Gone. And that evaporation is the heart of the information paradox. But the connection to thermodynamics, to entropy, came even a bit earlier, right? With Jacob Bekenstein.
Yes, Bekenstein was grappling with a related problem in the early 70s. He was worried about the second law of thermodynamics.
The law that says entropy disorder basically can never decrease in a closed system.
Right. Bekenstein realized black holes seem to violate this. What happens if you throw something with high entropy, like a cup of hot coffee, into a black hole?
The coffee disappears behind the horizon. Its entropy vanishes from our observable universe.
Looks like the total entropy just went down. A violation of the second law.
So Bekenstein had to save the law. What did he propose?
He made this incredibly bold suggestion. Maybe the black hole itself has entropy, and when something falls in, the black hole's own entropy increases enough to compensate, so the total entropy never decreases.
The black hole has entropy. How could you even define that?
He proposed what's now called the generalized second law, GSL. The total entropy is the entropy outside the black hole plus the black hole's own entropy. And crucially, he argued the black hole's entropy must be proportional to the area of its event horizon. Not its volume, its area.
Area. That's weird. Usually entropy scales with volume.
It was super weird. But then Hawking did his calculation. He found the black hole had a temperature. And in physics, if something has a temperature, it automatically has entropy. Hawking's calculation mathematically proved Bekenstein's formula. Entropy is proportional to area.
Wow. So Hawking confirmed Bekenstein, saved the second law, and showed black holes obey thermodynamics. A huge triumph.
A monumental triumph. But it immediately slammed them into the paradox with full force, because now we know the black hole has temperature, radiates, and evaporates completely.
Okay, let's walk through the fatal sequence now. You start with something ordered, low entropy, our star, or our library, a pure quantum state.
Right. It collapses into a black hole. Its entropy seems lost, but the black hole gains horizon area, so Bekenstein's entropy goes up. The GSL holds. So far, so good.
But then the black hole radiates, it shrinks, its area decreases, so its Bekenstein entropy decreases, and eventually it disappears entirely.
And what's left? Only the Hawking radiation. And Hawking's original calculation showed this radiation is perfectly thermal, random, characterized only by its temperature.
And a purely thermal state is the definition of maximum randomness, maximum entropy. It's called a mixed state. It contains basically no information about its origin.
Exactly. So you started with a highly specific, low entropy pure state, the star or library. It went through this process, and what came out was a completely generic high-entropy mixed state, the thermal radiation.
A pure state evolved into a mixed state in what should be a closed system.
And that is a catastrophic violation of unitarity. Quantum mechanics forbids that evolution. It means information was fundamentally destroyed. The final radiation has no memory of whether it came from a star or a library. Irreversible.
So the classical no-hair theorem made the black hole bald externally. Hawking's radiation calculation made the emission bald to featureless thermal noise. Gravity, combined with this first pass at quantum effects, really did look like the ultimate information shredder.
That's the technical core. This pure to mixed state transition, it cemented the paradox. Physics was officially broken. Yeah, physics is broken isn't something physicists take lightly. This contradiction ignited what Leonard Susskind perfectly termed the black hole war.
A war of ideas fought over decades.
Absolutely. And often quite personal, too. It was a fundamental clash over which pillar of physics was more sacred, which one had to bend or break.
So you had distinct factions forming. Let's talk about team information is lost. Who was leading that charge?
The most prominent figures were Stephen Hawking himself and also Kip Thorne. Their argument was essentially that gravity is just too powerful at the singularity.
They thought the singularity was a place where the usual rules just stopped applying.
Pretty much. They argued that the singularity represented a genuine boundary where quantum mechanics itself breaks down. That maybe trying to force unitarity to hold in such an extreme gravitational environment was a mistake. Perhaps information loss was just a necessary feature of quantum gravity.
A heavy price to pay, losing unitarity.
A huge price. But they felt maybe the consistency of gravity demanded it.
Okay, so who's on the other side? Team information is saved.
That camp was fiercely defended by people like Leonard Susskind, Gerard Hooft, another Nobel laureate, and John Preskill. Their position was absolutely firm.
What was their line in the sand?
Unitarity. That's the foundation. If you lose unitarity, you lose predictability, you lose causality, you basically lose physics as we know it. They argued that if something had to give way, it had to be general relativity. GR must be incomplete or need modification, not QM.
They were determined to find a mechanism, any mechanism, that let the information get out, to prove QM supreme.
Exactly. Make the world safe for quantum mechanics was their mantra.
And this conflict wasn't just academic papers. It spilled into public view with that famous bet in 1997.
Ah, the bet. Yes, Hawking and Thorne made a formal bet with John Preskill. The terms were clear. Is information lost when a black hole forms and evaporates, or is it ultimately recoverable?
And the prize was symbolic, right?
Perfectly symbolic. An encyclopedia, the winner's choice. Because an encyclopedia is, the embodiment of information that can be retrieved at will.
So who won the bet?
Well, technically, Preskill won. In 2004, at a conference in Dublin, Hawking publicly conceded. He admitted he'd been wrong, and that information should be preserved.
He actually gave Preskill an encyclopedia.
He did. Apparently it was a baseball encyclopedia, which Preskill found amusing as he wasn't a huge baseball fan. But Hawking conceded.
So, case closed. Information is saved.
Not quite. While Hawking conceded the principle, the actual mechanism he proposed in the paper, explaining his change of heart, let's just say it wasn't widely accepted. Most physicists felt it didn't really solve the how.
It was more of a philosophical concession than a physical solution?
Exactly. And that's where you get Suskind's rather pointed quote about Hawking.
Right, about being the soldier lost in the jungle after the war ended.
Yeah. Susskind felt that, from a theoretical standpoint, the war had actually been won years before Hawking conceded. Won not by a specific calculation for black holes, but by a revolutionary new principle in fundamental physics.
And that principle was the game changer. The holographic principle.
This was the turning point.
Right.
Proposed initially by Hooft and developed significantly by Susskind, it came directly from reflecting on Bekenstein's area law for black hole entropy.
Back to that weird finding that entropy scales with surface area, not volume.
Exactly, they asked. What if that's not just a fluke of black holes? What if it's a fundamental property of all space and gravity?
Meaning?
What?
That the information in a 3D space isn't stored in the volume.
That's the radical idea. The holographic principle suggests that all the information needed to describe a 3D volume of space can actually be fully encoded on its 2D boundary surface.
Like a hologram, a 3D image stored on a 2D film.
Precisely like a hologram. The idea is that our 3D universe might just be a holographic projection of information living on some distant 2D screen.
Okay, that's mind-bending. But how does that help with the information paradox, and how do you prove something like that?
Proving it rigorously was the challenge. The breakthrough came from Juan Maldacena in 1997 with his famous ATA-CFT correspondence.
ATA-CFT, anti-de Sitter conformal field theory. We need to unpack this. It's technical but crucial.
It is. It's the mathematical bedrock that convinced almost everyone, including eventually Hawking, that information must be saved.
So what is anti-de Sitter space, ADS?
It's a specific type of theoretical space-time geometry. Unlike our expanding universe, which is more like de Sitter space, ADS space has a negative curvature, which effectively acts like a boundary, a container. Think of it as a universe in a box.
Okay, so you have this ADS space-time box. What's inside?
Inside, in the bulk of the box, you have a theory of quantum gravity. It could be string theory or some other theory that includes gravity. It's complicated, involves fluctuating space-time, maybe even black holes forming and evaporating within this ADS space.
So the complex gravitational physics happens inside the box.
Right. Now, Maldacena discovered something astonishing. He found mathematical evidence for a duality and exact equivalence between this complicated theory of quantum gravity inside the d-dimensional ADS box and a much similar non-gravitational quantum field theory living purely on the d1-dimensional boundary of that box. This boundary theory is called a conformal field theory, CFT.
Wait, so the gravity theory inside and the non-gravity theory on the boundary are just two different mathematical descriptions of the same physical system?
Exactly. It's like having two different languages that can perfectly describe the same reality. Whatever happens in the gravitational bulk has a corresponding description in the boundary CFT and vice versa.
Okay, I think I see where this is going. What do we know about the boundary CFT?
The crucial thing is that the CFT on the boundary is a standard quantum field theory. It doesn't involve gravity's weirdness. And all standard quantum field theories are known to be unitary. They absolutely conserve information by their very construction.
So, if the boundary theory is unitary,
and it's just an equivalent description of the gravity theory inside the bulk,
then the gravity theory inside must also be unitary.
Bingo! That's the power of the duality. It proves by mathematical equivalence that quantum gravity, at least in these ADS spacetimes, has to conserve information. Unitarity is preserved.
It's a proof by proxy, almost. If the hologram film, CFT, is unitary, the 3D image gravity it projects must also respect unitarity.
That's a great way to put it. And this ADS-CFT result was so robust, so compelling, that it effectively ended the debate on whether information was lost. The consensus shifted dramatically.
Information is saved. Unitarity wins the war.
Unitarity wins. But as you said, this just opened up a new, arguably harder front in the war. Okay, fine, information is saved in principle, but how? How does it get out of a real black hole in our universe, which isn't ADS space? And what specific flaw in Hawking's original calculation allowed information to seemingly disappear?
The focus shifted from if to how, and that led to even deeper puzzles.
Right. So everyone accepts unitarity now, information gets out, but the how question immediately brings the focus away from the singularity, which is forever hidden anyway, right back to the event horizon.
Exactly. If information escapes, it has to somehow cross the horizon outwards, which seems impossible classically. And this is where Don Page's work becomes absolutely central.
Don Page, he quantified what information getting out actually looks like, didn't he? He did. He didn't focus on the energy or the particles themselves, but on the entanglement entropy of the Hawking radiation. He gave us a benchmark, a specific curve that any correct unitary theory of evaporation must produce.
Entanglement entropy. Let's clarify that again in this context. It's measuring.
It's measuring how much information is shared or locked up in the quantum correlations between the Hawking radiation that has escaped and the quantum state of the black hole that remains, or the radiation that hasn't escaped yet.
So if the radiation is perfectly thermal and random, like Hawking first thought,
then it's not really correlated with the black hole's internal state in a way that carries information. The entanglement entropy between the radiation and the hole would just keep increasing as more radiation is emitted, signifying the radiation is becoming more and more of a generic mixed state.
That's Hawking's original prediction, represented as a curve of entropy over time. It just goes up and stays high even after the black hole is gone.
Right. Monotonically increasing entropy, plateauing at a high value. That's the signature of information loss, a final mixed state.
But Page said, hold on. If unitarity is true, the final state must be pure. The radiation, once the black hole is completely gone, must contain all the information. Right. A pure state has zero entropy.
Exactly. So Page reasoned the entanglement entropy can't just keep going up forever. It must start at zero, before radiation begins, increase for a while as the black hole and radiation become entangled.
But then, crucially,
It must turn over and start decreasing, eventually going back down to zero when the evaporation is complete. This page curve, up, then down, is the unique signature of unitary evolution. The downturn means the later radiation is becoming entangled with the earlier radiation in just the right way to purify the whole state and encode the initial information.
and the point where the curve has to turn over, that has a name too.
The page time. He calculated when this turnover must happen, roughly when the black hole has evaporated away half of its initial mass, or perhaps more accurately, when half its initial entropy has been radiated.
Halfway through its life. And this was a huge deal. Why?
Because it meant the problem wasn't some obscure effect happening only when the black hole shrinks down to the tiny Planck scale, where we expect unknown quantum gravity effects. No, the discrepancy, the need for new physics, happens when the black hole is still huge.
The conflict between Hawking's calculation and what unitarity demands occurs long before the end, when space-time curvature is still relatively gentle near the horizon, where we thought we understood the physics.
Precisely. It meant that Hawking's semi-classical calculation, which combined known QFT with classical GR backgrounds, must be breaking down in a regime where it should have been reliable. That was deeply troubling.
So the battle lines were drawn again. Before the page time, entropy increases, everyone agrees. After the page time, Hawking's calculation says entropy keeps rising, but unitarity, the page curve, demands it must fall. Something new has to kick in after the page time to make that happen.
And the attempt to understand what kicks in led directly to maybe the most shocking proposal in the whole saga, the AMPS firewall.
AMPS Amhary, Marov, Polchinski, and Sully. Back in 2012, they took the page curve as gospel and followed its logical consequences.
They did. They basically said, okay, let's assume unitarity is absolutely true, the page curve is correct. What does that imply about the event horizon?
Yeah.
And the answer they found was violent.
They showed that you couldn't simultaneously hold on to three core principles of physics that everyone thought were true.
Right. It became a trilemma. You have three cherished principles. One, unitarity is true. Information is conserved. The page curve is right. Two, Einstein's equivalence principle holds at the horizon. An infalling observer experiences smooth space-time, no drama. Three, local quantum field theory is valid. Our standard low-energy physics works correctly near the horizon. AMPS argued you could have any two of these, but not all three.
You have to sacrifice one. Where does the contradiction arise?
It comes down to another fundamental quantum rule, the monogamy of entanglement.
Monogamy, like quantum particles can't be married to two partners at once.
Basically, yes. A quantum system can be maximally entangled with only one other system at a time. It can have partial entanglement with many, but it can only share its deepest maximal quantum connection with a single partner.
Okay. How does that apply at the event horizon? Let's use their ABC particle setup.
Okay, so imagine the black hole is past the page time. Now it emits a Hawking particle, let's call it B, which escapes.
B is the outgoing radiation particle.
Inside the black hole, there must be a partner particle, C, that B was initially entangled with. This is part of the mechanism that creates Hawking radiation in the first place.
C is the infalling partner.
Now, for the event horizon to be smooth and drama-free, principle 2, equivalence principle, particle B must be maximally entangled with its nearby partner C right as it's created at the horizon. This BC entanglement essentially smooths out the vacuum state there.
Okay, B is maximally entangled with C for a smooth ride.
But wait, we assumed unitarity holds. Principle 1, page curve. Because we are after the page time for the information to get out, the outgoing particle B must also be maximally entangled with all the Hawking radiation that escaped earlier. Let's call all that early radiation system A.
So B must also be maximally entangled with A, the early radiation, to carry the information out.
Exactly. So now we have particle B maximally entangled with partner C for smoothness, and maximally entangled with the early radiation A for unitarity.
It's entangled with two things at once.
Maximally entangled with two things. That violates the monogamy of entanglement. It's a quantum impossibility.
So AMPS said one of these entanglements has to go. Which one did they choose to break?
They argued that unitarity, the BA entanglement needed for the page curve, was non-negotiable. Therefore, the entanglement responsible for the smooth horizon, the BC entanglement, must be violently broken.
And breaking that entanglement means the horizon isn't smooth anymore.
It means it's catastrophically not smooth. To break the BC link requires an immense amount of energy right at the horizon. They proposed a firewall, a shell of incredibly high-energy particles sitting right at the event horizon.
A literal wall of fire.
Pretty much anything trying to fall into the black hole would hit this firewall and be instantly incinerated. It saves unitarity, but it completely violates Einstein's equivalence principle. And an falling observer would not have a smooth ride, they'd be fried.
Wow, so the choice was either information is lost, violate unitarity, or falling into a black hole is lethal right at the edge, violate equivalence principle.
That was the stark choice presented by the firewall paradox. It put the community in an incredibly uncomfortable position. Neither option seemed palatable. The war had reached a new level of crisis. The firewall paradox was deeply unsettling, but also incredibly productive. It forced physicists to look for a concrete mechanism that could save both unitarity and the smooth horizon. The answer couldn't just be philosophical, it had to be calculational.
And the resolution that finally emerged, really solidifying around 2019, involved finding a more sophisticated way to do the gravity calculations themselves. It wasn't about throwing GR out, but about applying it more carefully.
Exactly. But before we get to the core island idea, it's worth revisiting Hawking's last major contribution on this with Perry and Strominger, the soft hair idea.
Right, the idea that maybe black holes weren't perfectly bald after all. How did that fit in?
It was a step in the right direction.
Too.
By suggesting information was stored in these subtle zero-energy fields, soft hair, at the horizon, it opened the door to thinking the horizon wasn't just a passive boundary. They proposed that the escaping Hawking radiation wasn't purely thermal, but was subtly correlated with this soft hair, allowing information to leak out unitarily.
So it was an attempt to give the horizon some structure that could hold information.
Precisely. While the soft hair proposal itself didn't fully solve the problem or reproduce the page curve, it primed the pump for thinking about how the horizon region could play an active role in information retrieval.
Okay, so then came the big breakthrough in 2019. Papers started appearing that actually calculated the page curve using semi-classical gravity. How did they do it?
The key was using a more powerful tool from quantum gravity called the gravitational path integral, combined with insights from holography, 880 SCFT. This led them to a new way to calculate entropy, involving something called quantum extremal surfaces, QES.
Quantum extremal surfaces. Sounds complex.
It is, but the upshot was a revolutionary new rule for calculating the entanglement entropy of the Hawking radiation. It basically said, the old way Hawking calculated it is only part of the story.
What's the new rule?
The new rule, sometimes called the QES formula or the island rule, says that to find the true entropy of the radiation, you have to consider two possibilities and take the one that gives the minimum value.
Okay, two possibilities. What's possibility number one?
Possibility one is just a standard calculation. Find the entropy of the radiation system outside the black hole by itself. This is essentially what Hawking did, and it leads to the entropy always increasing. Let's call this the no-island contribution.
Standard calculation, entropy goes up. Got it. What's possibility two?
Possibility two is the radical new ingredient. It says you should calculate the entropy of the radiation plus the entropy of a region inside the black hole's event horizon. This region inside is called the island.
Whoa, wait. An island inside the black hole contributes to the entropy calculation of the radiation outside. That sounds completely non-local.
It is fundamentally non-local.
Wow.
That's the shock and the key insight. The rule says, find a region I, the island, inside the black hole, calculate the entropy of the radiation plus the entropy of this island, plus a term related to the island's boundary area, and find the island that minimizes this combined quantity.
Okay, so you have the no island value, Hawking's, and this new island value, and the true entropy is the minimum of those two.
Exactly. Now, think about how this plays out over the black hole's life.
Okay. Early on, the black hole's big. Lots of radiation hasn't come out yet.
Right. Early in the evaporation, before the page time, the entanglement between the inside and outside is growing. Calculating the entropy of the radiation alone, the no island value, gives a smaller number than any calculation involving a significant island inside.
So early on, the minimum value is the Hawking value. The entropy increases, just like Hawking said.
Correct. Hawking's calculation was perfectly fine for the first half of the black hole's life.
But then comes the page time. The black hole is half gone.
Now things switch. The black hole has shrunk considerably. The amount of radiation outside is large. At this point, the calculation that includes an island inside the shrinking black hole suddenly gives a smaller total entropy value than the no island calculation.
Why does including the island make the entropy smaller after the page time?
Because the island is inside the black hole. As the black hole continues to evaporate and shrink, the maximum possible size of this internal island also shrinks. The island's contribution to the entropy decreases. Since the island calculation is now the minimum, the total calculated entropy starts to track the shrinking island. It turns over and goes down.
Towards zero, as the black hole disappears entirely.
Exactly. The island rule automatically generates the page curve up, then down purely from a gravitational calculation. It shows how the information gets encoded in the radiation in a way consistent with unitarity.
That's incredible. It fixes the page curve. But what about the firewall? How does this island picture solve the AMPS paradox and the monogamy violation?
It solves it beautifully, almost trivially, once you accept the island rule. Remember the problem. Particle B outside was seemingly entangled with both particle C inside and the early radiation A.
The violation of monogamy.
The island rule basically says that after the page time, the region containing the infalling particle C, the island, is mathematically considered to be part of the same system as the external radiation A and B.
So C isn't truly inside and separate anymore in terms of information.
From the perspective of the entropy calculation, no. The island interior is effectively encoded in the distant radiation. Therefore, the entanglement between the outgoing particle B and its infalling partner C is no longer an entanglement between two separate systems, radiation versus black hole interior.
It's just internal entanglement within the larger radiation plus islands system.
Exactly. It's like the entanglement between your own two hands. It doesn't violate monogamy because it's all part of one quantum system. The BC entanglement is perfectly fine. It ensures the horizon is smooth. The BA entanglement is also fine, ensuring unitarity. There's no conflict.
So the island makes C part of the outside system, informationally speaking. The equivalence principle is saved, unitarity is saved, no firewall needed.
Precisely. The paradox dissolves because our definition of the systems involved was too naive, too local. Gravity itself, through this island mechanism, enforces a non-local connection.
Okay, but why is this island rule the correct rule? Where does it come from mathematically? You mentioned replica wormholes.
Right. The island rule isn't just pulled out of thin air. It's derived rigorously from the gravitational path integral. When you use the path integral to calculate the entropy more carefully, you find that after the page time, new types of spacetime geometries start to dominate the calculation.
Geometries that weren't included in Hawking's original calculation?
Exactly. These new geometries are called replica wormholes. They are Euclidean wormholes, sort of connections in imaginary time that link the interior of the black hole, the island region, directly to the distant radiation system.
So these mathematical wormholes provide the non-local connection.
They provide the mathematical justification for treating the island as part of the radiation system. The path integral automatically tells you to include these wormhole configurations, and when you do, the calculation naturally yields the island rule and reproduces the page curve. It's a stunning result, where gravity itself provides the mechanism to ensure quantum unitarity. #outro.
Wow, okay, so 50 years. A huge intellectual war. And the resolution is subtle but profound.
It really is. Unitarity stands, information is conserved. But it wasn't a simple case of QM just overwriting GR.
No, it seems like GR, when calculated more completely using these path integrals and wormholes, actually contains the seeds of its own salvation, you could say.
That's a good way to put it. Hawking's original semi-classical calculation wasn't wrong, it was just incomplete. It captured the physics before these new gravitational effects. The islands, represented by replica wormholes, became important after the page time.
So the black hole is the ultimate information scrambler, mixing things up incredibly well.
But it's not an information destroyer. The information does get out, encoded in incredibly subtle quantum correlations within the Hawking radiation, enabled by this unexpected non-local connection to the black hole interior.
And the biggest takeaway from all this, the really mind-altering implication.
It has to be about the nature of space-time itself. The fact that a region deep inside the black hole, the island, is somehow mathematically part of or encoded in the radiation system infinitely far away, that just shatters our intuitive picture of local reality.
Space-time isn't just a fixed background stage.
It seems not. It strongly suggests that space-time geometry, the very fabric of Einstein's general relativity, isn't fundamental. It's likely an emergent phenomenon.
Emergent from what?
Emergent from the more fundamental connections of quantum entanglement. The non-local threads of quantum information might literally be weaving the geometry of space-time itself.
So the information paradox wasn't just about black holes. It forced us to realize that gravity, GR, and quantum information, QM, aren't two separate things, but that gravity might actually be a macroscopic manifestation of quantum entanglement.
That seems to be the profound lesson. The black hole war didn't end with one theory defeating the other. It ended with the realization that they are deeply intrinsically linked, and that space and time might be, in some sense, an illusion built from quantum bits.
An illusion woven from pure quantum information. That's a staggering thought.
It truly is. And it leaves us, and you the listener, with a final provocative question to ponder. If something as seemingly fundamental as space and time can emerge from underlying quantum information,
What else about our reality? What other things we take for granted as fundamental building blocks might also be emergent properties, complex patterns arising from simpler, hidden quantum rules we haven't fully grasped yet?
what else is just part of the hologram?